Okay, so we've talked about that Coulomb force. And we have done examples here with individual charges, as in two charges. And we also looked a little bit at using symmetry.
And the two charges are just a small q and a big Q, right?
Yep. How sometimes symmetry can be used to simplify a problem. Today I want to look just a little bit more at a situation where we've got not symmetry but multiple charges. And so I'm going to grab a figure from the textbook here. And we're going to sort of use this as an example of what we would end up doing. And we're going to start off, as we always will in this particular course, looking at things first conceptually, then symbolically, and then calculations. So for this particular case, we've got individual little charges, which are the source charges, and then a single test charge out there. Now, as a reminder, that big Q test charge is also what we call our field point, and that will become clear when we start talking about electric field, as opposed to our test charges or our source charges. And when we have multiple charges, we're often going to label them things like Q1, Q2, Q3, Q4, ... Qi. And hopefully mathematically that makes sense to you. Each individual little charge is going to have some index.
And there can be letters with the Q's, right?
Yes. Okay. So these are going to be indexed. Now, eventually when we get to Python, we'll talk about indexing and all the rest of that kind of stuff, and we'll be able to create some arrays to do some of this kind of stuff. But what this means is that my R vector is my position of the field point, but my R prime, which is the position of the source point.
How are they different, the two R's? Like,
okay, so we'll hit this here in a second. Okay. There's multiple source points, and so there's multiple positions of those source points. Now, I'm going to grab here just a part of this diagram again so we can talk about this conceptually. I just have a hard time moving a large figure around on this particular program. Okay, so you could imagine that we have some coordinate system. And that coordinate system has some axis. And it's got some origin point. Now I'm going to do this in color. Our field point has a position relative to that coordinate system. Let me see here. It keeps trying to snap it to some sort of grid, which is making it difficult. But so that is the position of that field point. And so it has some x, y, z compared to the origin. Now, since this is flat on my paper, I'm really only doing x and y. Z would be if it was forwards or backwards from the paper. So we have full 3D. Each little charge, though, is going to have its own position. Which we call our R primes. Now, when we calculate the separation vector, then, the separation vectors go from the individual source charges to the test charge.
So
These are the separation. And again, this is my attempt to do a cursive R because I'm just not very good at drawing those neatly versus the regular R's, which are position vectors.
And you said prime is just for the ones.
Right. If we go and we look at the nomenclature in the textbook in our equation sheets, the primes are the source points, and the field points don't have the prime, and then the separation is the cursive R. Okay? Now there's a couple things I want to point out here to you guys. And I didn't leave myself a huge amount of room to do this. But I drew this axis for the origin independent of where my source charges and my test charges were. If I move this origin, it will change the position vectors, but it does not change the separation vectors. Because the separation vector goes from the source charge to the test charge, independent of where I put my origin. So when you're doing this, if you're given coordinates, that means somebody already set an origin and you use the x, y, z's and you find the differences between them. If you're not given an origin, depending on the diagram, you might set an origin that is convenient for the system. Okay? And I'm going to bring up a figure from the textbook and a problem that we'll work on a little bit when we get to electric field, where there's a similar sort of situation here. So in our textbook, after they get through these problems here. They've got one here that just had a random one, but then they've got this one. Now, they drew an axis here, but even if I didn't have an axis, it makes sense to put it where they put it. And so we'll talk about that here conceptually real quick. If I didn't have an axis, what I would have is I would have two test charges and a field point there. Well, it makes sense to draw an axis where these two are on a line. If that's on an axis, and this one is perpendicular to that axis, which I'm going to have to go back here and shift some of my stuff because...
So say if the two, the test charges, they was like the other way, like on top of each other, that's how you would make the line, the axis, like the...
So if I had, for example, two charges I could make a line here connecting them and a line perpendicular to that exactly in between them, and then put my field point out here. That would be a nice symmetry. So if your diagram has symmetry, it's nice to actually use that symmetry. Now, I could have taken this and moved it over, in which case, again, I've got two positions and a third position, but there's no symmetry there. That would be harder to set up my X, Y, and Z positions. By looking at this way, those are both on the X-axis, this is on the Y-axis. It's a lot easier to set up my XY coordinates. And the fact that it happens to be, which it doesn't necessarily have to be, but in this particular case, if I have equal distances, I also am going to have some nice symmetry in terms of the symmetry in the X direction. It's not symmetric in the Y direction, but it is symmetric in the X direction, which will simplify my problems. So my end statement here is if you see convenient axis symmetry type things, use it. Sometimes the problem is specified in such a way that you can't. But the separation vectors to find what I'm working with here do not depend on where I set my axes. So I might as well set them in convenient places. Okay? Now what we'll also see is that if you're doing it computationally, you can let the computer do the messy stuff in terms of calculating the vector separations. So you can set the coordinate system however it's most convenient for the problem, which might mean having an outside arbitrary point because that's how you've got the positions marked, okay? And so the math here, we don't have to set it so that it's convenient for the separations. We can just set it and let the computer deal with the messiness, okay? So conceptually, this is how we're working with setting up our axes. Now, stepping back for a minute though, we can also talk about the calculation. So when I have this figure, even if I'm doing this with the computer, I have to work with them in pairs. A source charge with a test charge. Okay? So you would go through on this.
Over there by M Market, by the 24-hour short range.
Now, what I mean by this work in pairs is that you will do one force calculation using charge 1 and the test charge, another calculation for force 2 and the test charge, another calculation for F3, and again, you have to do each of those arrows separately. And so these are going to give us 3 forces. So this one might be slightly in this direction, and then you might have this one, which is a little bit more in this direction, and then your next one might be somewhere in this direction. You know, as you're going through and doing things, I should redo that because I used the same color by accident twice.
Does it matter how you're going to, like, because you see, like, you're doing Q2 first instead of Q1. Does it matter?
It does not matter.
Okay.
So we'll state that here. Because in the end, you have to add all of those forces. And it's a vector sum. So really quickly, I'm going to make one new video